Hello everyone, welcome to RASAAYANA Institute of Sciences. In this video, we are going to discuss about the most important concept in organic chemistry, that is acidity of phenol. Okay, so generally phenol is aromatic alcohol. We can represent like this. This is a phenol. Okay, so phenol is acidic in nature. It is a pure acid. It is showing acidic character, acidic in nature. And phenol belongs to aromatic alcohol. Aromatic alcohol. It is a aromatic alcohol. So generally, if I take any phenol bearing with one proton, generally donating proton by any molecule is nothing but its acidity. Suppose see, this is a phenol. This phenol is going to lose one proton. After losing proton, there is a formation of a phenoxidine. This is called phenoxidine. Here O minus, and there is a net loss of H plus is observed. Now this is nothing but Ka. Ka nothing but acid dissociation constant. So when phenol loses one proton, there is a formation of phenoxidine. Phenol, this is phenoxide ion. So if you want to explain any molecule acidity, it is definitely depends only on stability of a phenoxidine. Otherwise, if any molecule acidity, if you want to compare, that is always depends on corresponding anion, which is formed after losing proton. So this is called conjugate base of this acid. So this acidity always depends on this stability. So indirectly I am saying that phenol acidity depends on stability of phenoxidine. It depends on stability of phenoxide ion. This is called phenoxidine. So this acidity depends on this one. If this is more stable, more acidic. Less stable, less acidic. So how this phenoxidine gets stabilized here? Now see, this is a phenoxidine. Phenoxidine involved in resonance. This is negative charge involving in resonance, and that negative charge is going to be present on carbon. This is delocalization stability. Here this is minus, this is double bond O. It is same way this negative charge migrate here, transfer to para position. The formed negative charges regularly keep on delocalizing, and the delocalize will increase electron density at ortho and para position. See, double bond, and here negative like this. These are the variable resonating structures of phenoxidine. So this phenoxidine is stabilized by this kind of resonating structures. The excess electrons present on this oxygen is distributed to ortho position, para position, one more ortho position. So these excess electrons not shared by meta position. So this is ortho, meta, and this is para. After formation of phenoxidine, the negative charge is distributed to ortho position, para position, one more ortho position. So finally I can say that the excess electron density on benzene, see, it is distributed like this. One negative charge is keep on delocalizing within the molecule. That excess electron density initially present on oxygen, then it is present on ortho position, one more ortho position, and one more para position. So at these particular positions, excess electron density is present. So this you can also write like this even. See, this is O, oxygen. Now these electrons are delocalizing from oxygen to complete aromatic ring, right? Now here, this oxygen sharing 1/4, and this carbon sharing 1/4 part, here 1/4 part, and here also 1/4 part. Which means, after formation of a phenoxidine, the excess electron density present on oxygen, it is shared by 2 ortho carbons and 1 para carbon. So that's why phenoxidine is more stable. Sharing partners are increases. After losing proton, there is a formation of a phenoxidine. This phenoxidine is stabilized by resonance. So finally I am saying that the excess electron density distributed are shared by 3 carbons and 1 oxygen. So that's why 1/4, 1/4, 1/4 like that. That's why phenoxidine is more stable. Finally phenol is more acidic. And you try to remember one key point. Ortho position carry more electron density. Then para position also carry more electron density, followed by one more ortho. Meta, there is no excess electron density. Suppose I want to increase stability of phenoxidine by substituting electron withdrawing groups over ortho position, para position, one more ortho position, this phenoxyetine stability is rapidly increases because negative ions are stabilized by electron withdrawing groups. Okay, so finally I am going to say that C, electron withdrawing groups increases stability. Electron withdrawing group increases stability and electron releasing groups decreases stability. Decreases stability of phenoxyetine. Every time remember target conjugate base here. It is a conjugate base of this acid. So I can say the negative ion which is formed, it is also called conjugate base. It is a conjugate base of phenol. Okay, that's why these two are called conjugate acid bases. Right? See this. So when negative charge is present at ortho position due to presence of electron withdrawing character, if this anion is stable, this is found to be more and more stable. And if you observe clearly, this negative charge is distributed at ortho positions and para. Now, if I substitute any withdrawing group at ortho position and one more at para position, this excess electron density is taken by that electron withdrawing group, then stability will be more and more increases. When stability rapidly increases, automatically this acidity also increases. So finally I can say that electron withdrawing groups increase stability and electron releasing group decreases stability of a phenoxyetine. Right? Next, see this. Now, suppose we know some selective groups here. Minus IE groups or minus ME groups generally are electron withdrawing groups. If these groups are present, acidity is increases. Minus IE or minus ME groups are electron withdrawing groups, increases acidity. That will increase acidity. So generally minus I nothing but sigma bond minus mesomeric effect, generally related to non-bonding as well as pi electron. Okay, so whenever phenol acidity compare with water molecule and any aliphatic alcohol. So here I am writing methanol. This is methanol. Now remember always phenol is more acidic than water molecule is more acidic than methanol. If I compare, this is 1, 2 and this is 3. So I can say first one is more acidic than second one is more acidic than third one. So generally aromatic alcohols are more acidic than water is more acidic than phenoxyetine. Reason behind is, see, when phenol is loses proton, there is a formation of a phenoxyetine. This is the one. And when water loses proton, there is a formation of a hydroxyetine. When methanol loses proton, there is a formation of methoxyetine. Remember, whichever anion is more stable, corresponding acid is more acidic. So if you compare the stability, phenoxyetine is more stable than hydroxide is more stable than methoxide. Especially see in this one, there is a resonance is observed here, but this two there is no resonance. Anion is not stabilized by any other factor. Additionally, see, hydrogen is a neutral atom, but methyl is a donor. Donor destabilizes the anion. So if you compare the stability, first one, second one and third one, first one is more stable than second one is more stable than third one. As stability increases, acidity also increases. So finally I can say that phenol is more acidic than water is more acidic than alcohol. Simply remember, water is more acidic than methanol. This point you remember. So it is also expressed in terms of acidity. Remember, Ka directly proportional to acidity. Okay? Suppose if you want to express in pKa inversely proportional to acidity. And what is the relation between Ka and pKa? Ka is inversely proportional to pKa. P inversely proportional to pKa. So in your examination, mostly they will ask questions in terms of Ka as well as pKa, but both for acidity basicity, mostly they are asking in case of pKa. Suppose if I want to express a question in terms of pKa, remember when pKa value increases, here I am writing value increases, then what happens? See, it is related to more basic in nature. Suppose see, when pKa value is regularly decreasing, okay, so these values are regularly decreasing, so this is belongs to acidic in nature. Means more pKa value more basic, less pKa value more acidic. Remember, when pKa value regularly decreasing, acidity increasing. When pKa value regularly increasing, basicity also increases. Okay, so here only one key point you need to remember for phenol. Phenol is acidic in nature due to resonance stabilized phenoxyanion. Phenoxyanion is stabilized by delocalization of negative charge, that excess electron density present at ortho and para positions. By substituting suitable withdrawing groups at ortho and para, acidity is rapidly increased. Okay, so if I take phenol and if I compare with a normal cyclohexanol, this is a normal cyclohexanol. Here generally phenol negative charge is stabilized by this benzene ring, but here negative charge is not stabilized by this one, so that's why this is more acidic than this one. And one more example, if I take phenol and by substituting a CH2 group over here, CH2 group. Now see, here this benzene is acts as a minus I group. Here it is minus I. Hydroxy not attaches to benzene directly, but here hydroxy attaches to benzene directly. That's why it is aromatic alcohol phenol. This is not phenol. So I can say still phenol is more acidic than phenyl methanol. This is called phenyl methanol. Right. See, if I take phenol and deuterated phenol, this is called deuterated phenol. Between these two, which is more acidic? Generally see, acidity depends upon the ability of donating proton. Here proton will be donated very easily, but not here. So the bond dissociation energy between oxygen and hydrogen is very less, but here it is very high. So due to presence of excess energy, it is not easy to donate deuterium. It can easy to donate hydrogen. So I can say first one is more acidic than deuterium. Okay, and if you compare any aliphatic alcohol, see, every aliphatic alcohol is less acidic than phenol. This is methanol, and here one more is ethanol. See this. Methanol is more acidic than ethanol, but methanol is less acidic than phenol because they are called aliphatic alcohols due to presence of donor. It is a donor. Donors destabilizes alcohol's acidity. Okay, so remember, aromatic alcohols are more acidic than aliphatic alcohols due to presence of donating character of alkyl groups. So indirectly, if I want to express alcohol's acidity, this is called primary and this is secondary. Okay, so alcohol acidity, if you compare, primary is more acidic than secondary, secondary is more acidic than tertiary. So this I will explain in other class, just you concentrate right now. Aliphatic alcohols, if you compare, primary alcohols are more acidic than secondary, secondary is more acidic than tertiary. Because tertiary carry a strong donor decreases acidity. Right, now see this. Few more examples I will explain. Suppose, generally phenol acidity depends upon electron withdrawing group or not? Yes. Now what I am saying is, if I substitute any electron withdrawing group and electron releasing groups in this particular phenol substitutions, see, here phenol having electron releasing group and here it is having a electron withdrawing group. Generally we know that if aromatic ring phenol, if there is a presence of an electron withdrawing group, acidity increases. So I can say that this is first one, second one, third one. Every time see, electron withdrawing group decrease electron density. Because phenol, after losing proton, you will get a phenoxyanion. Phenoxyanion having excess electron density, that excess electron density taken by withdrawing group. That's why it is more stable. So I can say second one is more acidic, then followed by first one, and then followed by third one. See the acidity order. This is acidity order. When this phenol loses proton, forms a phenoxyanion. Every time remember, if you want to explain acidity, first try to remove proton and think about conjugate base only. Every time conjugate base will explain the acidity. First remove proton, you will get negative ion. Here negative ion is present, it is delocalizing and giving excess electron density at ortho and para. This group is releasing electron. When they release electron, stability decreases. Already extra electrons are there. Releasing group is giving somewhat more extra electrons, that's why it is unstable. So finally I can say that 2 is more acidic than 1, 1 is more acidic than 2. 3 finally. Okay. Now observe clearly. I am giving some selective groups. Try to understand what is the nature of these two groups. See. Here I am writing OCH3 and here I am writing NO2. So what is the role of OCH3? That if you confirm clearly, then answer is closed. See, OCH3 is a mesomeric group. It is a plus mesomeric effect group. If any heteroatom directly connected to unsaturated group, it can release their non-bonding electrons clearly. Okay. So now already phenoxyanion, every time remember, remove proton, think about O minus. This O- is giving electrons at ortho. It is giving electrons at ortho. It is giving electrons at para. And one more is ortho. So already ring carry extra electron density. This group is giving somewhat more extra electrons. That's why this is unstable. Okay. But what happens? See, this position withdrawing group is present. It can withdraw maximum electron density more towards itself. This is found to be more stable. So I can say third one is more acidic as compared to first one. First one is more acidic as compared to second one. This is Ka order. You can also say either Ka order or acidity. pK is quite opposite. Okay. So whichever group is a strong donor whose acidity is very less. Remember, I am writing CH3 and I am writing alcohol. So which is a strongest donor? C. There is no donor. It is also donor. It is also donor. But hydroxy is a powerful donor. It is a powerful donor because it is a plus mesomeric effect group. And here it is only hyperconjugation and inductive effect has been considered. So mesomeric dominates inductive. Finally, I can say that these two having donor. So first one is more acidic than second one. Second one is more acidic than third one. This is the acidity order. Stronger the donor, weaker the acidity. Right. Suppose if I write hydroxy group here, hydroxy, then methoxy I am writing, then followed by hydrocarbon. Hydrocarbon I am going to write CH3. Now among these three, whichever molecule having a weakest donor. So three are donors here. It is a donor. And even this methoxy also donor, even methyl is also donor, inductive as well as hyperconjugation group. So, but out of these three, remember hydroxy is a powerful donor as compared to methoxy. Remember, methoxy is not a strong donor as compared to hydroxy. Hydroxy is a stronger donor as compared to methoxy. So I can say first one is least acidic. Third one is more acidic then it is a weakest donor. It is between these two, it is a weak donor. So I can say second one is more acidic than first one. Next, take few more. See, suppose in terms of withdrawing groups, here I am writing cyano and here I am writing nitro and here I am writing phenol with a corresponding substitution. Anyone you can write, that is aldehyde. So which is more acidic? Remember, nitro is the strongest withdrawing group as compared to cyano. Cyano is stronger than aldehyde. So finally I can say that second one is more acidic than first one is more acidic than third one. This is acidity order. When strength of withdrawing group increases, acidity also increases. Okay. Now I am going to take a molecule having a 2-nitro at ortho and para position, and I am writing a molecule at nitro and one more nitro over here. 3 withdrawing groups I am writing. And I am writing a molecule with only one withdrawing group, nitrate para position. So as number of withdrawing group increases, acidity increases. I can say second one is more acidic than first one followed by third one. More withdrawing groups, more acidity. Simply remember, relation for acidity and withdrawing groups is directly proportional. Suppose if any donating group is present, if donors increases, acidity decreases. This is CH3. Here 3 donors I given. Then I given a donor CH3 and here one more CH3. It is also a donor. Now this is CH3, only one donor. So methyl is an inductive group. It can release electron. Here only one donor, 2 donor, 3 donor. As number of donors increases, acidity decreases. So I can say third one is more acidic than second one is more acidic than first one. Okay. Next. Suppose if I take methyl groups at ortho position and I am taking a nitro group para, and here also remains same. Methyl group at meta position and I am using a nitro at meta para. This is para nitro, meta methyls are present. Now out of these two, which is more acidic? See, in this case this nitro is completely planar. This nitro you can also write like this. It is completely planar. Now these two are in plane. Benzene and nitro both are in plane. But what happens is due to steric crowding between this methyl and nitro is not planar. So with respect to benzene carbon nitro, it is non-planar. If it is non-planar, withdrawing character is very poor. If it is withdrawing very weakly, this acidic is very less. If it is withdrawing very strongly, its acidity is very high. So 1 is more acidic than 2. Okay. So if I take any halogens, remember, this is fluorobenzene. Here this is chlorobenzene. And bromo I am writing, then followed by complete iodobenzene. Out of this 4C, generally greater the withdrawing character, greater the acidity. But generally see, chlorobenzene is a powerful withdrawing group as compared to fluorobenzene. Because see, fluorobenzene having a 2p electrons, and here also 2p overlap is there. But what happens is this is 3p, and here additionally 3d empty orbital is present. So this chlorine having a improper overlap with this 2p orbital of carbon. That's why chlorine additional 2 factors are there. Due to presence of unequal size and due to presence of empty 3d orbital, chlorine acts as a strong withdrawing group as compared to fluorine. So finally I can say that second one is more acidic than fluorobenzene. Then later on bromobenzene, third one, then followed by fourth one. This is many times asked in exam. This is very, very important one. When any halogen attaches to benzene, both effects are present. Okay. So halogen is acts as a plus mesomeric effect group. It is same way minus inductive effect group. Through sigma bond it can withdraw electron. Through non-bonding it can donate electron. Inductive mesomeric both are present. But remember, inductive effect minus inductive effect is going to dominate plus mesomeric effect for halogens. So that's why when halogens are present on aromatic rings, try to operate only inductive effect. Don't operate mesomeric effect for halogens only. Right? This is very, very important example. Chlorobenzene more acidic as compared to fluoro, then followed by bromo and iodo. Okay. Now see, this is one of the example where regularly asking in examination. Orthonitro, next I am writing metanitro. Now next paranitro. Out of these 3, which is more acidic? See, when negative charge delocalizing in phenoxidine, it is giving more electron density at para, then ortho, and then meta. Para having more electron density. When para having more electron density, para withdrawing group is more stable. Later on ortho, later on meta. So I can say third one is more acidic than second one and then first one. Okay, ortho, meta, para competition comes. If ring carry extra electron density, if that extra electron density distributed at para and ortho positions, especially para having more electron cloud as compared to ortho. Ortho para. So this I will show. See in this case. See the resonance form. In this resonance form, see, ortho carry extra electron density, para carry extra electron density, one more ortho carry extra electron density. When negative charge is delocalizing around benzene, para should carry more extra electron density as compared to 2 ortho positions. Okay. So don't think that, sir, here 2 ortho positions carry negative, negative, they carry more extra electron density. Not. Actually, para having more extra electron density as compared to 2 ortho positions. Okay. So always negative charge, if it is present at para, it should be more dominative as compared to negative charge present at ortho. Right? Now see, based on that we can explain like this. See, para having more extra electron density, it is withdrawing conveniently. More extra electron density if it is taken by nitro, it is found to be more stable. More stable, more acidic. Suppose if any donating group if I give, this is OCH3 donating group, and here one more donating group at meta, and here one more donating group at para. Now can you say which is more acidic among this? Remember, if withdrawing group is present, acidity increases. When donating group is present, acidity decreases. So we know that para position more electron density already appeared over here, and this group is giving somewhat more extra electron density. That's why it is highly unstable. So I can say this is highly unstable, later on this and this. So finally I can say that second one is more acidic than first one is more acidic than third one. Okay. Now suppose if I take any hydrocarbons, This is ortho position hydrocarbon, meta position hydrocarbon, then followed by para position hydrocarbon. Everything will be exceptions over here. Now see, I given three different positions of methyl group here. Methyl at ortho position is a powerful donor. Methyl can release more extra electron density at ortho position only as compared to para. Even though negative charge is delocalizing at para effectively, but methyl release more electron density at ortho. Ortho carry more electron density as compared to para. Now, as compared to these two, this carry less electron density. So I can say second one is more acidic as compared to third one is more acidic as compared to first one. Because first one, due to presence of methyl group at ortho position, it is the strongest donor as compared to para. Okay, and very important point already explained, that when any halogen is present at ortho, and one more is meta and para, always try to operate only inductive effect. Don't operate mesomeric effect. Okay, only distance factor we need to consider when halogens attaches to ortho, meta and para. So distance factor, see, this halogen is very close to phenol hydroxy group. Now this halogen is moving far away. Here see, this fluorine is moving far away. As distance increases, inductive effect decreases. So this fluorine is a strong withdrawing group as compared to this one as well as this one. So when halogens are present, remember, always operate inductive effect. Inductive effect nothing but only distance, see. So like that distance we need to cover. It is withdrawing from large distance. It is withdrawing from very large distance. When distance increases, automatically we know that withdrawing capacity is very poor. So I can say first one is more acidic than second and then third. When halogens are present, be careful. Now I can also explain based on chloro. See, orthochloro. This is simple example. You can work out this. So answer is remain same. Here don't see positions. See distance only. Here it is very closer. It is moving little away. It is moving far away from each other. So I can say first one, second one, third one. Answer is remain same. Acidic character of these three is remain same every time. Okay. Now, so this is nitro. Here hydroxy group. This is cyano and this is nitro, and here I am writing aldehyde. So what is the acidity order of these three? See, between nitro, cyano, which is strong, it may be ortho or para position. Three ortho positions we need to compare. So nitro is very stronger than cyano. Cyano is very stronger than aldehyde. So that is the answer. Okay. Now, suppose if you want to explain their basicity, okay, remember phenol forms a phenoxidine. This is phenoxidine when they given nitro group. Ortho para positions like this. This is asked in examination. This is meta position and this is para position. Okay. So now I want to explain pKa order. pKa order. So what is the correct pKa order? I am not asking about acidity. When negative ion is present for phenol, that negative ion becomes a conjugate base. So when conjugate base is given, they will ask about basicity order. Now, whichever position having a strongest withdrawing group, lone pair is not available. So we know already very well, nitro is a powerful withdrawing group at para, later on ortho, later on meta. Greater the pKa value, greater the basicity. So withdrawing groups decrease basicity. Ability of donating lone pair is called basicity. So this withdrawing group will take more extra electron density, then availability of this lone pair is very poor. So it is a powerful withdrawing group, later on this one, later on this one. So pK value is very high for that particular base where lone pair is available. In which among these three lone pair is available? Second one having more availability of lone pair, then later on first one having more availability of lone pair as compared to third one. So this is pK order. pK order nothing but it is reverse to acidity. Means the ability of donating lone pair of electron, that is called pKa. Okay. Suppose if I take this molecule with a donor, this is OCH3 methoxy group, meta position, and here one more meta position. Now, when negative charge is given, go for conjugate base. Now what happens, see, these groups can release electrons more effectively from para. Later on, more electrons from ortho. Very less electron density from meta position. Electron density, if you compare negative n, how much ability is there for this negative n to available for any acid is called basicity. That is pKa value. More availability, more basicity. Okay, when negative n is given, question related to basicity. When any proton is available, question related to acidity. Now in this case, due to presence of more extra electron density, this negative charge is more available. Because methoxy is a powerful donor from para. Later on ortho, later on meta. So I want to write pKa order, basicity order, which is more basic. Third one is more basic than first one. First one is more basic than second one. Strong donor, moderate donor, weak donor. So as donating ability increases, pKa values are very high. So pKa value is directly proportional to basicity, inversely proportional to acidity. Okay, so two possible questions you can expect, either from Ka or pKa. Okay, so that is about concept of phenol acidity. So take a short revision. See, acidity of phenol, it is a general structure of phenol. Generally phenol is acidic in nature, it is also called aromatic alcohol. This acidity depends on this base. It is called phenoxyanion. This phenoxyanion is stabilized by resonance like this. Whenever if it is involving in resonance, that negative charge is distributed at ortho and para positions only. So whenever if it is giving electrons to ortho, para and one more ortho, that excess electron density available at para position only, not at ortho. Para having more electron density as compared to ortho. Ortho having more electron density as compared to meta. See that negative charge is not clearly present on meta position. So that's why I can say that when this negative charge is delocalizing around the aromatic ring, this negative charge availability is very high on para, later on ortho. Okay, so that's why para having more electron cloud as compared to ortho and meta. So generally when negative charge is delocalizing, we can stabilize that negative charge by substituting electron withdrawing groups. Indirectly I am saying that electron withdrawing groups increase stability as well as acidity. Then go through this. So minus I, minus M increase acidity. Okay, so these are the general examples. This is stable because resonance. Here these two don't have any resonance. Here no donor, here donor. That's why it is unstable, least acidic. These are the general terms of Ka and pK regarding acidity, and primary, secondary, tertiary alcohols acidity order. It is primary, secondary, tertiary acidity order of alcohols. Acidity of alcohols. Okay, so this is a general scale of pKa. Then rough examples are given regarding acidity of phenol. Okay, so withdrawing groups increase acidity, neutral and releasing groups. Some examples are given: releasing group, withdrawing group. Releasing group, releasing group. It is a strong withdrawing group, strong donor, weak donor. Powerful donor, moderate donor, weak donor. So donors decrease acidity. Out of these three, it is the weakest donor. So that's why it is more acidic. 3. Next. So if you see, some electron withdrawing groups are given with different positions and multiple number of electron withdrawing groups with a proper strong withdrawing group, moderate withdrawing group and weak withdrawing group. Different possibilities are given. Okay. Then nitro group are given. It is a perfectly planar with benzene. If any withdrawing group is planar with benzene, whose withdrawing capacity is very strong. That's why it is a powerful withdrawing group, more acidic as compared to this. This is very important one. Generally when halogens attaches to benzene, don't apply mesomeric effect. Inductive dominates mesomeric. And that too, fluorine is a strong inductive as compared to chlorine. Chlorine is strong inductive as compared to bromine and iodine. But if you compare the two factors, there is a presence of 3d orbital and 3p. But here there is no 2d. If you compare overall factors, chlorine is a strong withdrawing group as compared to fluorine. That's why this is more acidic as compared to this, later on this and this. So these are the general order. And these are few more examples with proper electron withdrawing groups at ortho, meta, para, donors at ortho, meta, para, donors at ortho, meta, para. Here also same. Withdrawing groups, if halogen is present, go for the distance. See distance, very closer, moving away, moving far away, like that. Okay. So finally this is the conclusion. You will see the pKa, reverse means see, first when proton loosed by phenol, you will get conjugate base. That conjugate basicity I am explaining. That basicity depends on donor. Acidity depends on withdrawing group. Basicity depends upon the donor. It is the strongest donor. It is the weakest, sorry. It is the strongest donor. It is the strongest withdrawing groups. So we know donating group increase basicity, withdrawing group decrease basicity. Okay. So that is about concept of phenol acidity. That is the maximum information I given. So hope you will understand. Try to subscribe our channel so that such kind of complete subject information is going to be given regularly in the form of notification if you subscribe, so that you can see the video as early as possible, and that will be helpful for your IIT mains, advanced as well as NEET examination. Okay. So thank you for watching. Okay. So thank you for subscribing our channel.